This is a 2024 GIT problem that appeared in the electrical engineering paper and is on BJT biasing. So here's the problem statement. A BJT biasing circuit is shown in the figure below, where VBE is equal to 0.7 volt and beta equal to 100. The quiescent point values of VCE and IC are respectively option A 4.6 volt and 2.46 milliampere, option B 2.61 volt and 3.13 milliampere, option C 4.6 volt and 3.13 milliampere, and option D is 3.5 volt and 2.46 milliampere. And this is the corresponding circuit. So it's a typical voltage divider based bias circuit. R1 is equal to 100 kilo ohm and this is 50 kilo ohm R2, and the collector resistance is 2 kilo ohms and the emitter resistance is equal to 1 kilo ohm, and the biasing voltage is equal to 12 volts. The other end of this is connected to ground. So our objective is to find out the collector current IC and the collector to emitter voltage drop. So these are the Q point values. The way to go about solving this sort of circuit is as follows. So first of all, what you have to do is to separate out the voltage sources just for the ease of convenience. So we can have this 12 volt source and then 100 kilo ohm and 50 kilo ohm. This is forming a voltage divider circuit. And then you should treat the right hand part, that means the BJT followed by the RC and the RE along with the supply voltage. So treat this as the load network and try to obtain the Thevenin's equivalent circuit for this left hand part. And this is easy to find because what we can do is we can open out this load and then try to look into the circuit and find out the open circuit voltage or the Thevenin's equivalent voltage, and this will be equal to 50 kilo ohms divided by 100 kilo ohms plus 50 kilo ohms into 12 volt, which is the voltage for a typical voltage divider, and this turns out to be 4 volt. Whereas if you want to find out the R Thevenin, then looking into this terminal, so the load is open circuited, this is not present. We are looking into this terminal having connected this DC voltage source to ground. So we are suppressing this DC voltage source or deactivating it from our circuit in order to find out the equivalent resistance, and then we find that here is a 50 kilo ohm that goes to ground and there is another 100 kilo ohm that also goes to ground, and so the equivalent voltage will be this 100 kilo ohm in parallel to the 50 kilo ohm, and this turns out to be 33.33 kilo ohms. So once we have managed to obtain the Thevenin's equivalent circuit for the left hand part of our entire DC biasing network, we can go ahead and make the substitution, which is shown over here. So this is your VTH, which is 4 volts, and the Thevenin resistance RTH, so this is equal to 33.33 kilo ohms, and then this is connected to the base terminal. So basically this becomes the base resistance. RTH can also be thought of as a base resistance, and then the rest of the load network is reconnected, and now we should go about solving for this circuit. So in the next part, what we have to do is to look at this path, that means starting from this VTH through RTH, then VBE and RE to ground. So we are looking at this loop and we should try to obtain the KVL equation for this. Our objective is to find out the base current from this loop. So we write VTH minus of, if I call this current as IB, then IB times RTH minus of VBE minus of IB multiplied by beta plus 1 multiplied by RE. Note that IE is equal to beta plus 1. So this is the net expression. Otherwise, we could have also written it like so. So you could have written it like IB. We look at this voltage, starting voltage is VTH. What is the other drop? Other drop is base to emitter voltage drop, and then divide it by the resistances. So one of them is RTH, but the other one, RE, should be multiplied by the factor of beta plus 1, because we are looking into the network where this is basically an amplified version. This current is an amplified version of the base current, and the amplification factor is beta plus 1. So we go about, plug in the values. So VTH is equal to 4 volts. VP is mentioned in the question as 0.7. RTH we obtained as 33.33 kilo ohms. Beta is mentioned in the problem as 100. So 100 plus 1 multiplied by 1 kilo ohm. RE is given in the problem. So this is RE is equal to 1 kilo ohm. And from here we obtain the value of IB. IB is equal to 0.02456 milliampere. And if you want to obtain IC, which is one of the quiescent values of the circuit, this is simply beta times IB. And therefore, if beta is equal to 100, the collector current comes out to be 2.46 milliampere approximately. So this gives us the value of IC. So the left-hand part of the network allows us to evaluate for IB, and if we obtain IB, we can easily obtain IC and IE. Now from the right-hand part of the network, so we are now going to consider this part of our circuit. So that means we start with VCC, then there is a voltage drop across RC, then there is this drop of VCE, and again there is a drop across RE. So we are considering this loop now, and we can frame the KVL expression because our target is now to find out the value of VCE. So VCC minus of IC times RC minus of this drop VCE minus of IE times RE. And we note the fact that IC is equal to beta IB and IE is equal to beta plus 1 times IB. And therefore we can make those substitutions here. And because all the values are known to us, VCC is known, beta is given, IB we had determined, RC is given. Again, beta plus 1 will be 101. RE is mentioned in the problem as 1 kilo ohm, and then IB we have determined. So simply plugging in the values, we obtain the approximate value of VCE as 4.6 volts. So as for the problem given to us, option A is the correct answer. So if I have to quickly sum up what we did with this sort of a problem, we were given a voltage divider network. We found out the equivalent Thevenin's model for the left-hand part of the circuit, that means the divider unit, and then we used this loop to obtain the value of IB and hence IC as also IE, and then use the right-hand part of the loop to obtain the value of VCE. This is the general scheme for solving any sort of BJT biasing circuits which are based on this voltage divider.